Welcome everyone to today's video on chapter 13. This is going to be the fourth video on this chapter. In this video we're going to talk more about solubility and how it's impacted by temperature and pressure. So start off, talk about solubility and temperature here. Here we have this plot. On here is the solubility of a bunch of different salts versus temperature, right? We see in general for almost every salt here, right, the solubility increases with increasing temperature. Some more rapidly than others, but in general things increase with increasing temperature. Now there's the very rare case of something like the cesium sulfate salt that has the opposite trend, with decreasing solubility with decreasing temperature, but in general, as you increase temperature, the solubility increases for a salt. Okay? And you think of just that in increasing temperature, you have more energy available in your system to break apart these intermolecular forces between solute, and solvent particles to make it easier for them to separate and mix together. Okay? Right, and on this chart we can also look at these plots of solubilities and discuss here where we have regions that are soluble, where in this region we have saturated and unsaturated and supersaturated solutions, right? So if we focus on something like sodium chloride, right? So this line here, sodium chloride, okay, right? That line represents a saturated solution, right? The solubility of a salt is its saturation limit. How much salt can I dissolve in a solution and have it fully dissolved, right? And so that sodium chloride, right, is saying that I can roughly dissolve, like, say, 32 grams of sodium chloride in every 100 grams of water, okay? That's its solubility, right? I can't dissolve any more of that in water, and if I dissolve less, it will completely dissolve, and that will form an unsaturated solution, right? So this is saturated, right? This is unsaturated, right? And then if you form a solution above the saturation line, right, this would be the super saturated solutions, right? Often how one forms a supersaturated solution is you take advantage of this temperature effect of solubility, and say for sodium chloride, you heat this thing up to near 100 degrees Celsius, right? The solubility is now 40 grams of sodium chloride per 100 grams of water, and then you slowly cool your system down to, say room temperature or something like that, right? And you do it very slowly and very carefully, and often you can keep that. Everything that's been dissolved in that solution will stay dissolved, and you'll form a supersaturated solution, but again, it will not be very stable. And if you do anything to perturb this solution, it can eventually kind of crash out a bunch of solid salt until you reach a saturated solution again. Okay. For gases, you actually kind of have the inverse effect of solubility and temperature, right? So here you have the solubility of a bunch of gases in water, okay? And you see that this solubility decreases with increasing temperature, okay? And the reason for that is, right, in order for a gas to dissolve in a solution, right, that gas needs to hit the solution and then get trapped inside the solution, right? And the faster these gases are moving around, the more energy they have, the less likely they're going to hit a solution and get trapped in there and stay inside that solution, right? Because if they have more energy, right, if they're in the solution, they're going to be moving around a lot, and they're more likely to escape from that solution. And so that's why their solubility decreases with increasing temperature. Okay. With pressure, okay, solids typically don't have really much of an effect, right, that pressure on their solubility. For gases, tend to have an increase in pressure corresponds to an increase in solubility. Okay. kind of show why this is through this picture here, right, where I'm looking at the solubility of carbon dioxide in water. Okay, I have some system where I have a bunch of gas particles, right, of carbon dioxide, and some of them are dissolved in the solution, right? And at the surface, you sometimes have these gas particles going into the solution. After they hit the solution, they dissolve, and some of these gas particles in the solution will escape from the surface of the solution, right? And I'm in this kind of state where I have the same number of particles going in and out of solution, right? And I have this saturated solution, okay? Well, if I increase the pressure, right, what's going to happen is I now have more particles hitting the surface of the solution, right? I used to have just a couple of particles at a time hitting the surface, but now I got a bunch more particles hitting this surface, right? So now each one of these particles has a chance of getting trapped, right? Well, that just means the more particles that hit that surface, right, the more particles that will get trapped, okay? And so the number of particles that get stuck in solution then is going to increase, right, until I reach a state where I then eventually have the same number of particles going in solution as they do coming out of solution, again, like we did initially, right? Okay, because as I trap more particles in solution, right, it reduces the number of particles that are hitting the surface and getting trapped, and then it increases the number of particles in solution that can escape back to the gas, right? So eventually I'll re-reach this state of equilibrium where I have the same number of particles transferring in and out of solution, right? And I have a now increased amount of gas particles in my solution because of that increase in pressure. Okay. The mathematical description of this relationship between solubility of a gas and pressure of that gas is given by Henry's law. Okay. Henry's law is given by this relationship. S is the solubility of the gas, okay, equals K times the pressure of the gas, right? So K is Henry's law constant. It is a constant number, but it depends on what solute and solvent you're talking about, right? If you're talking about carbon dioxide and water, if you're talking about methane and water, it depends on the solute and solvent combination, okay? So that constant is unique for each solute-solvent combination, is often determined in the lab, okay? And then reported in some set of tables and things like that, like those in your book. Okay? And again, P here is the pressure of the gas, and S here is the solubility of the gas. Okay. So we note this linear relationship between solubility and pressure. So as you say double the pressure of the gas, you double its solubility. Okay. And you can just see a plot of this, right? If you were to plot the pressure of that gas versus its solubility, you'd see this linear relationship right here, right? The blue line. Okay. And often this is done in lab to where then the slope of this line is related with Henry's law's constant. Okay. And so in lab, that's how often you determine what this value of K is by measuring the pressure of the gas and measuring its solubility in that solution and making this type of a plot to then measure what K is. Okay? And so that's it for how temperature and pressure affect the solubility of solids and gases in a solution.